Well, it's wonderful to be here. I usually think of Elon with a certain level of distaste because you are like the problem of our soccer team. And I don't remember if it's men or women's or both, but it's like all I hear is Elon. And then it's just so, it was nice today to be like Elon. And so, anyway, you have a very good soccer team, which I know every year from playoffs that they live in fear of. They wouldn't like that I say that, but they do. And so my name is Tim Chartier. And one of the things with this talk that's a little different than sometimes is often I'm asked just to share on like sports ranking and things like that, or just to share on the Mime show. So you're going to get both. And I'm going to try to move a little faster in the Mime show on the verbal part, because clearly I'm not just silent, so that you can see a few more pieces, because that's often what people enjoy. So these are my two worlds in terms of mathematics. This is actually the logo for the sports analytics group that just started this semester at Davidson. So I'm working with 3 students, and we're working with the men's basketball team. So tomorrow at noon, we're going to meet 2 of the coaches, as we do every week, and we talk about the sports analytics that we're developing for them. We have ideas, and then they correct our ideas, because they know the sport much better than we do. At the same time, we know what's possible, and so we talk about what we can do, and then they talk about what they want to know. And then they were so excited that they asked us to start a Twitter account. So we're actually tweeting, and we had 150 people follow us in one day. So it's not very often as a mathematician you feel heavily liked and affirmed. So that was a nice day. So this is what I'm going to talk about. We're going to start over here with some sports ranking and try to give you a feel for what that is. I'm not going to go into a lot of detail. If you want to know how to do it, I will show you where to go. And you'll actually see where to go, and you can still see me because it's online. Then we'll move to Mime. This is Marcel Marceau, who is like Michael Jordan to the Michael Jordan's power in Mime. There would be no Mime in many ways without him. And my wife and I were lucky enough to train with him multiple times. So some of the pieces you see will have that element in it. So first of all, sports analytics. What's that about? What is it for? It's a rising and huge part of sports right now. In the NBA, they just signed a contract that they have these video cameras, 6 of them at the top of every arena, and every 25th of a second, they're snapping a picture. That's not really a picture. They're grabbing data off of the pictures for 13 people, because there are 10 players playing the game, and then there are 3 referees. So they get an XY coordinate for each and every person, and then they get an XYZ coordinate for the ball every 25th of a second. That's actually better resolution than a film. A film that you're watching is 24 frames per second, except The Hobbit, which some people aren't sure was a good choice on their part. But nonetheless, it's not as good as a video game. I learned that video games are 48 frames per second, which was kind of intriguing. I'm not sure why we need more, but you may know, but let's not talk about that. But anyway, that's what they're doing. And how big is that file for a basketball game, for the NBA? It's a 40 megabyte text file. In other words, it's honking huge amount of data they have no idea what to do with. They're super excited, but they do not know exactly what to do with it. So that we are in an era of those types of things. If you have interests in math, it's an era where you can move into that. There's a group in Charlotte named Redventure who hires a lot of Davidson students, maybe because they're close and they know we're there, but why not hire Elon students? You could interview with them, and they do analytics, not for sports, but for other types of things. And again, their name is Redventure, if you were interested in that. They also have summer internships as well. So what I do, one of the areas, I do several things, but this is my main area, is that I do sports ranking. Well, that's the ever-present question. Who's number 1? But it's very different with what I do, because I'm interested in who's number 2, and 3, and 5, and 8, and 13. Generally, though, the question is why? Wait a minute, why are you trying to figure out? I don't care whose number is 13. That's actually not true. I care who's number 13. But it could be like, why do you care what's number 13? That's when I feel like a mathematician, because I can and I want to know. That's actually not true. You would want to know, too, if you were doing the work we were doing, because it helps you predict. Not that you have to look like that to predict, but nonetheless, it helps you predict. Why? Well, the reason why is easily seen in March Madness. We've done this for March Madness, and what we do is we rank all the teams that are playing. By ranking them, you then know who you, as a mathematical technique, predict will win. Because the number 1 ranked team will beat everybody. Number 2 will beat everybody except the number 1 team. So you immediately know what your method has done. I won't show you the personalized method because it's just too much to try. I'll speak to it very briefly. I'll bring it up because a couple of you mentioned ranking, so I'll give you a sense of how it's done. But I do March Madness both for math majors and non-math majors. In fact, given my art world, my performing arts friends who are uber haters of math do it as well. Okay? So how hard can it be? I mean, you've got 1 ball, 2 nets, and 64 teams. And what's going on? It's just March Madness. That's true, but the problem is if you're not familiar with this, if you're such a academic or whatever it is that you have no idea what March Madness is, then there are only 50 million people participating, but that doesn't need to be you. But for a moment, we do need to figure out what's going on. What happens is on Selection Sunday, which is generally right around March 15th, they determine who those initial matchups are. That's all the information you're given. And then what you need to do to fill out a bracket is that you determine who you think is going to win in each one of these pairwise matchups. Then you have who you thought would win. And then from your 2 predictions, who do you think will then predict, who do you then predict will win, and so forth and so on. Okay? You actually start with about 68 teams, but they actually say you don't have to predict the first couple until they get to 64. So that's why it's 64. So you start with 64, then you go to 32, then you go to 16 and 4, until finally you get the number 1. So you still are predicting who's number 1. But to have a good bracket, you have to do much more than predict the winner. You have to get a lot more of the teams as it's moving on. Okay? So to give you a sense of what we've done with this madness, I don't know if a lot of students don't know that reference, but at least the faculty are enjoying the moment of nostalgia. This is Mad Magazine, and this is the main character. My sister was a big reader of Mad Magazine. ESPN hosts an online tournament. There are several tournaments, so if you wanted to do this, you wouldn't need to do ESPN. It's just probably the most popular. And we do it mainly because, like last year was 8 million different brackets were submitted. You fill out a bracket, and you know how your bracket does versus other brackets. So you know what percentile you're in, which is why we do it, because it's fun to see. Oh, but that's the one thing. If you're an athlete, you can't do it because until you're a senior, you're not going to play anymore. Because if you win, you get $10,000. So if you have a perfect bracket, you get $1 million. There's never been a perfect bracket done on any online challenge at all. It's almost impossible to do, which can not seem like it should be, but there are, I don't even remember what the number is of how many brackets are possible. You can look it up. It's on the Huffington Post. I put it in one article in there. But last year there were 8 million brackets submitted. Then my students create these math-based brackets and see how they do. The problem with the whole thing, and that's the madness, are these upsets. So this is Steph Curry, who played for Davidson when we made the Elite 8. And this is Steph in front of our main academic building. I don't know if this was when he was a student or when he came back. Davidson, to graduate from Davidson, you have to take so many classes your senior year on campus, which was Steph's major issue, because he left before his senior year to become a millionaire, to play NBA basketball. And he's a great guy. He comes back to Davidson. This blew my mind. Last summer, he ran a basketball camp for kids K to 3, 5 to 8-year-olds. That just blew my mind. It's like the guy, it's like people pay. Well, people were paying, but not much. Just to, you probably don't have children yet, and because you're in college and so forth and so on. But I do. And I watch my daughter, she'd have a blast doing it, but I can guarantee she's never making it in the net. It's some amalgamation. It's just some kind of combination between occasionally soccer, a little bit of wrestling, and then occasionally you'll teach her some basketball. Because if the ball's she's not dribbling, she's just going to kick that thing. If you're in the way, she might just tackle you. So there's some football. If you don't stay down, then she's going to wrestle you and so forth. And that's who he wanted to work with. He said, I want to work with them because that's when you can affect them as a person. And that's Steph Curry. But he helped us get to that level, and that was a big year. And our methods probably would not have predicted that Davidson would do that well. It would be nice to say that they would, but some of the upsets are just very difficult to discern. So the way that it works is that what we do is that you have teams. So this is Davidson, and this is Kansas. And the way that we represent what happens is using what's called graph theory. And you have the team, and you point to the team that wins. You could do it the other way, but this is the bad sportsmanship graph where it's I beat you. And I'm not only doing that, I'm talking about a game that was 2 years ago. But I still like to point out to my KU friends that we beat you. So we're very proud of that game. And that's the way it works. Okay? So this is the graph of NCAA men's Division I basketball. And the question is, looking at this graph, who do you think is going to win? Exactly. That's why you need math to do it. Now, sometimes people are wondering who these people are. I'm not really sure, but this took a long time to run on my computer just to get that with every game in Division I. So that's why we use math to do it. And what we use are methods used within the BCS, which is the Bowl Championship Series. So that's going to go away because they're changing the way they're doing it. But two of the methods actually use linear algebra. Now, if you're a math student, you've probably taken linear algebra. You may not. Students don't always remember it, but they remember doing it, but they don't always remember what it was. If you're not a math student, you did algebra, linear algebra, just you might not have called it that. In like elementary, well, it wasn't elementary, it was probably middle school to high school. There was x plus 2y equal 5, and x minus y equals 10. That's linear algebra. You have two unknowns, x and y. What values for x and y make those two equations both true? I don't know. Exactly, they're unknowns, okay? Same thing here, but instead of two unknowns, we have 350 unknowns for 350 equations, because that's how many teams we're doing, okay? Once you have that, if this is the ranking, where Davidson, of course, is number 1, then I put Furman, and then Charleston, and then App State. If this was a small little tournament, then once you have your ranking, you know who you think's going to win. Is that if Davidson's playing Charleston, then who is going to win? Davidson, because they're ranked number 1. Between Furman and App, it's going to be Furman. And then I also know that the overall winner, according to my ranking, will be Davidson. It's that easy, okay? That's why you can do it. So when you have this, if you were to do what we do, you would have 5,000 games. So you're going to use a computer to do it. At Davidson, we use MATLAB. Why? Because that's what I do my research in, and I wrote the code. Here, you could use Mathematica. You just have to change the code a little bit, and I'll show you where you could go to do that and to actually get it to run. Or you can actually use some online code that I have, too. Now, I have some Java applets that do it as well. Okay? So really quick, just to show you how this works, we submitted them to ESPN. The first year, there were 4 million brackets. The second year, there were 5 million. Last year, there were 8 million. And this is how we did. So in 2009, I was working with Eric, and we just weren't even sure this was going to work. So we created our brackets, and our best bracket was in the 97th percentile out of 4 million. The next year was a homework assignment given to students. They learned this in 3 days. The best one was 99th percentile. He was also valedictorian of the entire school, but that doesn't count. So then the next year was the hardest year because that was the year with George Mason. It was just a year of a lot of upsets. And we were in the 78th or 79th percentile, which can sound crummy, but we actually couldn't find any sports expert that did better than us. Doesn't mean there wasn't one, but the point being when you looked around, you just couldn't find anybody. So it was really people who were fans of those teams and happened to put them in their brackets who were beating us. So that's how we've done. One thing that's fun about this is you don't have to be a sports fan to actually do well. Kelly won one year. She got free books from Princeton University Press. These aren't the books she picked. These are my books, but nonetheless, it got the picture. And then Ben & Jerry's gives a free cone to whoever wins the bracket. They're more excited about this than any other part of the class. So, but Kelly won, and Kelly knows almost nothing about basketball. Usually it's a non-basketball fan who wins, because basketball fans, if you think back to here, when you're doing it, they'll look at who's going to win. And for instance, people who just can't stand Duke, it doesn't matter what they come up with. They're not going to keep a bracket that says Duke wins. They just won't do it, so they keep changing it. Kelly didn't really care, so she just came up with math and then created her bracket. Okay? We've adapted this to a lot of different settings. If any of these are interesting to you, I can point you to them, but I only have 2 more slides on this, then we'll move to mine. Is that, so you saw basketball. We've done other things with basketball, but that's the main one I'll refer to. We have used it in the NFL. So what we did in the NFL was that we incorporated ties into the method. And any time a game was within 3 points, we treated it as a tie. So if you and I play and we're within 3 points, we said, no, 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 we're going to treat that exactly as a tie. And it actually predicted better over 10 years. It was better 9 of the 10 years, and the other year it was just as good. So that was intriguing. Baseball, we actually did, well, I wasn't actually part of this work, but the group at Furman that I work with, they did it for players. So pitchers are competing with batters, and you treat that as a game. And they were able to rank pitchers and batters, and they were actually able to find people pitchers in particular, who were pitching really well, but you didn't see it in their ERA and so forth because the people behind them were not playing very well. They weren't on a very good team, and when they were traded, they suddenly just did amazingly well. So that was that. NASCAR we just did this summer, where we were using it to rank NASCAR players rather than the point system that they use. And we were actually able to to predict who would be in the chase, which is the playoffs of NASCAR, earlier than the point system that they actually use, which was very surprising. Prediculous is an online group that hired us to do ranking for them. It's a game where you predict. So they would say, who's going to win? Is UVA or Davidson going to win on Saturday? And then you predict, and then according to your predictions, you get ranked. So we did work for them. The last one's Twitter. We created an algorithm to rank Twitter accounts. So it's similar to Google. I'll actually talk about Google in the Mime show, but it's very similar to the idea of which web pages are better when you put in a query. We were doing that for Twitter users. And Davidson submitted a patent on that work, which you can argue whether that's a good thing or not, but whatever, they own it, so they can choose what they want to do with it. So if any of that's interesting, I can send you toward it. But if you want to do the ranking itself, you can go to Udemy. It's an online, and I have an online course. It's free. You just sign up, and you can learn to do sports ranking. It walks you through. So this is very important. I don't know who all is in the audience, but I know at least we have one English person because they're an English professor. So. And you may be totally into the math, and that's fine, but just I don't know. And, but if you want to learn this, some of the lectures are just anyone can watch that and enjoy it. Then there are the more math, like more math. That means you may have no idea what I'm talking about if you have not taken math recently. And I don't hold back on the notation and so forth. So if you're really math geekified, then those are fun. If not, then skip them and just move on. You don't have to know how to do it. Okay? And then next year, Davidson's joined edX for 2 years, and I'm going to do a MOOC on applications of linear algebra, of which this will be part of it. And so you can look for that next spring if that's of any interest. It's not a credit thing. You just would be an add-on that you could do. So this is what I told you. I wanted to tell you this one part because a couple of you brought it up, that you're doing ranking. So with ranking, it all comes down to the following, is that in these systems, you determine how much is a game worth. Normally, when you rank, every game's worth 1. So if we're playing ping pong for whatever reason, and we're so into math, we're going to use these methods to rank our ping pong tournament, which, whatever. But, I mean, we've all had math word problems. 2 trains going in 2 opposite directions. When will they collide? I don't know. When will they actually say, maybe we should stop? So anyway, so if we're playing this, and we play, and you win, and I lose, you won 1 game, I lost 1 game. The way that you alter the method is you just ask yourself, let's not do that. Let's say that early in the season, those are not very predictive of how you're going to play in March Madness. So rather than at that time, we played this like 3 years ago when you were just coming in and you had a ping pong table at home and you were just on fire with ping pong. We're going to act like that's 1/10 of a game. So even though you beat me, you still get something for that. We don't just omit the data, but you get 1/10 of a point and I lose 1/10 of you win 1/10 of a game, I lose 1/10 of a game. But in the same way, you can say right up to the tournament, that's not just 1 game, that's 5 games, maybe 10 games. And it's worth a lot. That's how our methods can find teams that really don't have the best record in the world, but right at the end, they're not only hot, but they're beating really good teams consistently all at the end. And then boom, we say, no, they're going to beat this other team. Every year in the first round, most of my students are in the 80 to 90th percentile in that first round of games because there's not a whole lot of difference there, but it means we found 1 or 2 upsets that most people in the country did not predict, which is fun. You're just using math. There's something fun about that. Okay? So anyway, that's the sports ranking stuff, and you can turn to that resource if you want more detail. So now let's turn to the other part of my life, Mime. I promise I won't talk as much in that part. And this is, of course, Marcel Marceau. And so what I want to do first is I want to just connect, how does mime possibly have anything to do with math? Well, first we need to actually see some mime. And rather than just sit here and be placid as if we are in math class, you actually are going to participate a little bit. And so I'm going to actually teach you a mime illusion. Now, I need to tell you that it takes practice. So if you start getting self-conscious, just don't worry about it. Just try. Because why not? I mean, you've been possibly in math class, like you're ever going to do that right the first time. If you did, then think of another time, because we all just eventually do it wrong. I'm a math professor. You know, all this research sounds phenomenal. Yeah, but that was like the 1% of the time it actually worked. The other 99% of the time, it's like, man, this is just like, we created a ranking method once where it actually was better to lose. Like we had it, we're like, this is great. And then we did it, and it was like the losing team went, pfft. It was like, I think something's wrong with that. And then we did it again. We kept looking at it. We're like, no, this actually makes sense. Okay, that doesn't. But the method makes sense. And it took us a month and a half to figure out what was wrong. What was wrong? If you're a mathematician, you'll understand. I don't know if you're not a mathematician, you'll understand what I mean. But we looked at the derivation of the method, and the model we used didn't fit. It broke the derivation, so it broke the whole method. And so nothing would ever work. So that's just part of it. So here we go. What I'm going to do, my hands are cold, so I don't know exactly what this looks like for you. But this is the wall, which most people know. If you're going to think of mime, you're going to make fun of a mime, you're probably going to make fun of that or them leaning. So, okay. Are my hands turning lighter when I hit the wall? They may not. My hands are pretty cold. Well, whatever. It looks good because you didn't even respond to that. So, all right. Okay, that's the one I want to teach you. Okay, then I'll connect it to math because you are using mathematical thinking in it. Doesn't mean you're using calculus. If you are, good for you. Let's not talk about that. But you don't have to be to do it. Okay, so take your hands and you actually put them on your head. So if you really worked at your hair, you're allowed to just kind of act like it. You can mime putting them on your head. Now take them off and look at them. Okay, this is the position your hands go in when they're not on the wall. Okay, this is very important. You are not a blockhead. Your head is not like this. Because otherwise, you're going to do a wall like this. It just kind of looks like you put your hands on the wall and then you just like took the wall with you. You know, it's like, what was that? Okay, so they're slightly rounded. The other one, this is the one dancers like to do. It's like people who dance, they like to do this. Really? That doesn't look oh yeah, it does. It's like this, like, what are you doing? I don't know, man, but I like the wall. It's like, that's just odd looking, all right? Really formally trained dancers do the waterbed. It's just like, what is that? I don't know, man. It's really cool, though. It's like, all right, whatever, all right? Okay, so your hands are slightly rounded. Remember, you can always check. I'd like to point out to kids just to see if they get the joke. If you can't check, you got another problem. That's a great joke to give in middle school because they all go, ha, and that's it. But anyway, all right, so there you go. Now bring your hands in front of you, and on the count of 3, you're going to flatten your hand as best you can. Okay? 1, 2, 3, flatten. Now you actually look at your hand. I'm not because I'm looking at you, but you look at your hand and see if it looks flat. Now for those of you who are very far along in your math training, let's just go for a generalistic sense of flatness. Let's not spend an hour trying to work on this, okay? But part of what you're trying to figure out is what does it take for your hand to be flat? Why? Because watch my hand for a moment. My hand actually overextends. My wife's hand, she's a very good mime. Tanya's hand, her name's Tanya. Tanya's hand does not. So when Tanya hits that wall, man, she can just like smack it as hard as she wants, and her hand will always be, but like right now, I'm not talking as clearly because I'm smacking it, and my brain's going, don't go all the way. And so like that, okay? So look at your hand again. Go flat. Now look at it and see if you can get it. Like that time, I didn't actually go flat. Okay, now bring them in front. Rounded, you can check. Bring them down. 1, 2, 3, flatten. Now, this is the trick. Now you only take one hand off the wall at a time. You can take them both off, but when you do, the wall disappears. Okay? Not really, but I mean, it's like, wow, dude, I like mime physics. Okay, so here we go. All right, so you take one hand off, and what does, it goes into skull position. That's called skull position or head position. Okay? It's not that. It's not carpal tunnel hand. Okay? All right, so here we go. It comes off. Good. Flatten. Good. Take it off. Flatten. Okay, let me teach you one more thing. That was really good. So the last thing is I'm going to teach you is what's called, we call it talk, which I don't know why. But what talk is the robot, basically, is that when you do the robot, you can be stiff the whole time. And you can go, ugh, and be stiff and then stop. People do that, but it kind of looks like, I don't know, it just looks like you're exercising. And a better way to do it is with talk, it's essentially a jerk, is that you go like that, and then you stop. Okay, so let me do it without talking. It'll be a little better, easier for me. That wasn't the best, but it was the basic idea. Okay, that's what you want to do when your hand hits the wall, if you can. You watch my hand. I didn't do it for you at first because in mime school, it actually is a fairly elite, prestigious thing if you can do it without doing talk. Okay, so right now I'm being a snooty mime. Okay. Okay. Okay, does everybody see what I'm saying, though? That I'm not doing that. What I want you to do is this. Do you see how it's just like, it'll make, when you're not really good at it, there's something about that that just makes it look better. Okay, so try it. Just do your own. Don't do it with me. Just try your own pace. Yeah, hold on. I only know how to do it if I start there. That's fine. Okay, good. All right. All right, so there's one more thing I need to do with you, because it won't be a mime show unless we all do the box together. So from now on, when somebody makes fun of a mime, they're making fun of you too. So you can join the community. And if you make fun of a mime, I don't mind now, because you're making fun of yourself. So it's not a big deal. All right, so put your hands in front. You're on the wall. Then you're going to go to the side. It's a little tricky when your chairs are this close, but just be aware of each other, okay? By the way, if you are, I don't know how much teaching training you have here, but if you're a teacher, this is what you don't do with middle school students. Turn to the side, how you doing? You know, it's just like, you just don't do that. And if it's kids, it's like, sorry. You know what I mean? So you just go to the ceiling, but I'll do it the side for you. So one hand comes off at a time, right? So you only do one hand to the side. Now the side is established, so you can put the other hand on the side. This is harder because now you can see me in profile, so I've got to be a little more careful on the wall. Yours is really hard because you're both doing it at each other, so you're trying to actually try to keep a consistent distance, but it looks good. Now go up and make your ceiling. Okay, you try that rather than watching me. Oh, good, that looks good. They're relatively flat. All right, that's good. It's always interesting watching when somebody becomes self-aware. It's like you're totally in a wall, it's looking good, then all of a sudden it's just like, it's just like, you looked good until you did that. You know what I mean? It's like, wow, you look self-conscious right now. And so Marceau used to say that when we trained for him, because he'd ask you to do pieces for him. He'd say, can you do that for me? Man, if you did that, you had to be in the moment fully. Because if at any level, any internal dialogue happened, at any level, the audience will see it. The best example I have of that was he asked me to do the stare illusion. I'm not that great at it, so I'm not going to do it for you. I might do a tiny, tiny bit, but not the full exercise, because I'll just be too self-aware. And but I hadn't done it in like 5 months. He goes, come up in front of the class and show the class the stairs illusion. And I'm like, oh my gosh. But no, and it sounds kind of Jedi-ish, but it's what you do in mime school, is you refer to your teacher as master. So I said, yes, master. And so I stood up, went to the front, and then, let me see if I can remember how to do that. Yeah, so I was going, that's not quite right, but whatever. And I was going up the stairs, and I go over, and then when you're doing it, can you just stand up a second? So I'm going to act like you're me. So you just turn around, and we're going to act like you're doing the mime thing called stand there. So you're right there. And if I'm Marceau, he's literally like right here. He's going, oh, very good, but you can't pay attention to that. You just have to stand there. And so for me, it was do the wall, and he's watching the whole thing. Okay. So the whole time, I'm sitting there going up. He's watching me. And I'm like, man, this is going really well. He's like, this is great. And then I'm coming down the stairs. You do it in 8 steps, and you do a semicircle. I'm coming down the steps. I'm like, this is great. Then all of a sudden it hits me. I can't remember how to do the last step. I have no idea. I have 4 steps left. I'm going, crud, how do you do the last step? I don't know, do something. Oh, very good, very good. Do something. I don't know what to do. And all of a sudden I get to the last step, and I'm just like, just do it. So I have my positioning. There it is. I have my positioning. I get to the last step. I actually did it right. I mean, I just did something. I was like, whatever, just, sin boldly. So I just get off, and I go, and this hand drops. So watch very carefully. Let me get into more teaching positioning. So, today we're doing differential equations and so forth. And then like mime, you elevate. You'll see it in the pieces. You actually suspend. You suspend. It's hard for me not to suspend myself since I'm doing the mime for you already. But I drop this hand, and Marceau goes, freeze. So and that's what you do when you're told. You just freeze. And you stay there until he's done. So he goes, right now, there are 5,000 people watching you. And then he comes up to this hand. He goes, and they're all looking at that hand. And he goes, why? And that meant I could then say something. And I said, because it's the only part that's not suspended. And he goes, exactly. And they're all trying to figure out, what are you doing with that hand? What are you doing with that hand? Nothing, because I forgot. Exactly. Do it again. And so I'm doing the whole stairs again, and then so forth, and I came off. The one thing I will say to you about that is in life, when you don't know what to do, don't just let internal dialogue control you. Just do it. and you will discover sometimes your own unique voice. That was not the case there. I was supposed to sound like him and look like him, but that can be the case in other settings. All right, so I have an opening piece for you, just for us to move. Oh, I'm sorry, I didn't connect that to math. Let me connect the one part to math. There are two basic math principles you're using. One is just spatial thinking. You made a flat wall. You don't need to. You can make it into a sphere or an ellipsoid or whatever you want, like that, which could make it a balloon. There's several of you, more in general, are physics, so you can give it elasticity. And it comes back like that. You can push like that. That's exactly how you can go up, and you can go, and then you can lean like that if you want. Or you can go over here, use the spatial. That's a little high, but I can adjust, and so forth and so on. Okay? You can even make it where it's something else. So you're like you're in the dark, and then you bump into something, and then you finally figure out it's, in fact, someone, and something like that. All right? The other thing that you probably noticed when you did it is that often people worry that their hands aren't perfect. Oh, they need to be perfect. That's the one thing I want you to know, is that when you do the wall, it doesn't need to be, particularly if you're doing the talk. It can be pretty off. Like right now, there. Right now, I'm off in terms of the distance, and I'm not making my hand particularly flat. But you probably still see it as a wall. Marceau, when he performed, purposely did not do the wall well. And one time in class, someone said, "Master, why do you not do the wall well in performance?" And he wasn't offended because we knew that he wasn't. He said, because I do not want people to be sitting and watching how beautiful is the illusion. No, the important part is not that I'm touching the wall. The important part is why I'm touching the wall. So that's a good moment for an English professor. You can think about that for a little while. So the math people are like, yeah, but technically, anyway, no. All right, so I want to do this sketch for you. I'm going to be a conductor, and this is going to be my baton. And you're going to be my audience. And this connects to the idea of just counting. I want to teach you a magic trick in a second. And so the way it's going to work is I'm going to bring the baton down, and you're going to clap one time together. So before I'm the character with the baton, I just want to try it so that we can actually do it together. Okay? So we'll just do it with my hand right now. And good. And we'll try to do it more together. Here we go. That's better. That's very good. Okay, now you're ready. All right. So let me turn the mic off so you don't have to hear me doing whatever it is I do as a silent mime. Big ones is just counting. It's just counting to one and getting that down. The other is looking for patterns. But I want to show you a magic trick that connects to just counting. Oh, I'm sorry, I forgot to turn the mic back on. So those of you in video land, you'll just have to infer from my moving mouth what I was saying. So here we go. Is that what I want you to do is I want you to pick a number between 10 and 20, okay? Whatever it is. And you're going to start right down here on this penny, and you're going to count. So for instance, if I had 11, I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and keep track of where I landed. All right, can you try that? So count backwards. This is a magic trick of Martin Gardner, who is a very prolific writer and not a math professor, but a real lover of math among many other things, including magic and actually Alice in Wonderland. Did you find where you were? Okay? Okay, so keep track of that. I'm going to get rid of the bottom. And wherever you are, so if I landed here, that's where I count backwards from, but I count that as 1. So if I'm right here and I'm counting back, I count to the same number. I start in here and I go 1, 2, 3. So if I'm here, I go 1, 2, 3, and count back, or count up to your number again. So if I had 11, I'd count up to 11 and see in here where you land. Okay? Did you get it? I think you're the first audience where very few of you are using your fingers. Normally people actually use their fingers a lot. It was a math professor using the finger mainly, but normally a lot of other people do. Is that where you are? So the first time I ever did this, I did it for my calculus class. I was going to be performing it that night for what are called Celebration of Mind events. These are events held worldwide to celebrate the writer Martin Gardner. So if you wanted to have one, like, you could even have one still this year. They typically are in October to celebrate what would have been his birthday. He lived a long life into his 90s and passed away a few years ago. Well, we were going to do our Mime-matics show, and we wanted to do this trick in order to honor Martin Gardner. But I wasn't really sure how it would go, because even though it may seem like mimes are kind of magical, I don't do magic really. And so I did this for my calc class just to see how it went. I got to the last slide, and I said, so now, through the magic of calculus, I predict you are here. And when I did that, it was like this collective, oh. Then all of a sudden, like over in the left, this small little group started laughing and all turning and looking at a student named Kevin, which in teacher, when you go to teacher school, you means Kevin just cracked a joke. Okay? Kevin was a great guy, nice student. It's Davidson, probably like Elon, we kind of know each other, so I just said, Kevin just isn't the kind of student that you would feel, it was funny, and he isn't going to mind sharing it. So I said, Kevin, do you mind sharing what happened? He goes, you know, I know for everyone else that you just showed that you are magical, and you've just got this keen sense of us, and you're putting the fear of your ability to read our minds. For me, you just reminded me that I can't follow directions. And so Kevin graduates this year, and hopefully he's done a better job of following directions than this particular magic trick. But anyway, it's a fun trick. Let's talk about why it works, so if you want to do it later, you could. All right? Let's go back to the beginning. When you're counting, let's do 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm right there. Now I'm going to count back. 1, 2, 3. How many pennies do I have left? No matter what happened, no matter where I was here, once I land there, I'm going to keep going here. But how many do I have left? I always have 8 because that's what would have taken me down to there, right? 1, 2, 3, 4, 5, 6, 7, 8. So I'd be here, and I'd always have 8 left. 1, 2, 3, 4, 5, 6, 7, 8. Right there. And that's what's predicted. Okay? So you don't have to memorize anything. You don't have to know how many are up here. You don't have to know how many are in the tail. And you can do the trick yourself. It's a cool trick. Well, I will tell you one thing. It works better when you do it with a lot of people like I just did. Because if someone doesn't follow directions, you're not going to predict what they did. And the one I will tell you if you want to try this is right here when I said, if this is where you're pointing, you go 1, 2, 3. That's the only confusing part of the trick, is counting where you're pointing as number 1, if you know what I'm saying. Otherwise, they're going to count a different length. Okay. I want to now talk about infinity. So we counted, and a lot of people think of that as math. If I'm on a plane, what do? I teach. What do you teach? And there's that defining moment. How long is this conversation about to go? Okay? I teach math. Then we wait. We either enter a discussion of mimes where no one talks, or we enter a psychological evaluation where they core dump all negative mathematical experiences on me, or they like to prove their whatever levels of education they have in mathematics and tell me everything they possibly know about math, some of which I usually don't even actually know myself. And it's like, okay, and that's where it is. But if people, by and large, if they've not studied much math, they'll say, you know what? I was really good at arithmetic. Oh, okay. I don't say this, but this is what always goes through my head. What do you think I got a PhD in exactly? I added a gigantic number to another gigantic number that nobody had ever added before. And I got a ride. And so it's like, holy cow, what are you thinking, man? And so, but at the same time, that's what math is. Like Michaela the other day, my daughter, Michaela, she said, you know what? In this parking lot holds a lot of cars. You're right, it does. I counted how many the other day. You did? Yes. How many did you count? 100. Really? Yeah. No, actually, I counted to 20, but it felt like 100. I was like, I can understand that. I think my students do that sometimes. Are you grading this one? What do you not say? No. Are you grading this one? No. I felt like I did the whole answer. There you go. I'm done with that one, all right? But this sketch is to help you begin to think about math in the ways that a mathematician can think about it if you never have. Mathematicians think about infinity. What's there to think about? It means infinitely big. Yes, but there's much more that through the lens of math you can analyze. So to help us with that, we're going to imagine that on the floor there is an infinite rope. And it goes forever in this direction and goes forever in this direction. Okay? We'll watch that, and then I'm going to ask you a question at the end. So I'm going to take the mic off because this is a fairly physical sketch. I think I can do it in these pants. I wore deeper pocket pants today, partially for that. All right, so let's try this sketch. All right, I have one question for you related to that. There are two parts of it that relate to infinity. I'll only briefly refer to the second one. This is why mimes don't talk, so give me a second, I'll be there. But there's the part in the sketch where the rope goes on forever in both directions. The mime, me, grabs the rope, okay? I take scissors and I cut it, and a rather large part of it goes away. How much rope, do not answer out loud if you can possibly help it. How much rope do I have left in my hand? Okay, that's the question. Do either of you have an answer for that? How much rope would you say is in my hand? Do you have an answer? You don't need to. It's just you're beyond the youngest here, so I just wanted to give you a shot. Do you have an answer? No? Can anybody think what answers I would tend to get, particularly from large elementary school shows? What do you think? Half. Not even half of infinity. Half. That's one I get. What's another one? I call it the safe college student answer. No offense. A lot. Yeah, there you go. A lot. Yeah, okay. I got one 2 weeks ago at a local school. The child said 1 inch. That's a great teachable moment, unless you have nothing to say. An inch. Anyone else? Can anybody think? It took me a moment to figure it out. Can you think why? Yeah. I figured it out after a moment. I said, I actually didn't just move on. I went, oh, yes. The amount in my hand, right there's an inch. He's like, yeah. I'm like, all right. Any other answers for any other part of the rope? And then eventually someone, they will say infinitely, but generally not. They'll say it still goes on forever. But in that same group, the 1 inch group, I got another answer that was amazing. I'd never heard this before. Now let me see how did they do that? How much of the rope do I have left in my hand? Oh yeah, the same amount that went away except flipped over. Can you think it? Same amount, but flipped over. That was an awesome answer. So I did it for 2 shows. That was lower L that did that. That was K through 2. Then 3 through 5. 5, you never know. 5th graders, they're there or not there, but they're with the 3rd graders. So sometimes it's like, dude, I'm too cool to, I'm going into 6th grade soon. And so you just kind of have to let it be what it's going to be. So the last part that has infinity, just to kind of connect that for you, is at the end of the sketch, I cut the rope, I cut it in half and in half and in half. And then that part where I go like this is supposed to just conjure an image, whether it does or not is its own thing. It's to conjure an image of infinitely many cuts. And that's to represent that infinity doesn't just mean huge size. That even on the number line between 0 and 1, there are infinitely many numbers. And that's its own discussion as well. But that's in there for you too. All right. All right, give me a second to, I'm going to unplug this for a second. Or I better not do that. Let me just move forward on a few slides. So this part is, I'll just talk you through these quickly, but I'm going to let that sketch go because I'm going to run out of time and I want to be sure I can show you the other things. One thing that's interesting, somebody in this group was mentioning they were working on compression and with fractals. And so the way that I teach people what compression is within what I do is I point out that people do compression all the time when they do Sudoku puzzles. Sudoku is a form of compression in that you have only 24 numbers that encode the position of 81 numbers. But to do it, you have to know the rules of the game. This is standard Sudoku, and that's what's called pyramid Sudoku. How you blow it back up. So this is shrunk down. This is compressed. To decompress, you have to know the rules of the game that compressed it. If you like Sudoku, you can actually get this particular book. It's called Color Sudoku, and it's by Laura Tallman of James Madison University, who's a math professor. She does research on Sudoku as well, and there are different styles of puzzles. If you're a computer science person, her husband, Philip, did the coding to actually be sure that all of these only have one solution, which is fun. They have a second book. It was called Naked Sudoku. It wasn't a statement on how you should do it. What it meant was there are no initial numbers. There's nothing. And then the rules of the game would have only one solution. The book, because of the title, people were never sure. They always got, like Laura would go to a bookstore and watch people, and they'd like, get the book and be like, and it's just Sudoku puzzles, but now, oh. And so it didn't sell real well. But you can't find that one anymore. But one thing with compression is that in these, it gives you everything back. One thing about standard compression is it usually doesn't. It gives you a lot of it back, but not all of it, which the work that you were mentioning is to have higher resolution in it. Which of these pictures is lower resolution? Can you tell? Yeah, the one on the left. This one only uses 17.5% of storage. And that's so that it would like cross the internet, go through space if it was from a Mars rover. And I could see if there's anything I think I might be interested in. If you've taken linear algebra, this actually just uses what's called a singular value decomposition. Which if you've never done that, it's just 3 matrices that when multiplied equal the one I want. Okay? The second quick thing is Google is an application of math. And to give you a quick sense of how Google works is you can think of it as interviewing when I get down to 2 people. And I've asked them both for 3 references. Who would you hire? Well, it can feel like you'd hire this person because they have 3. But what if you were creating a Windows lab with PCs and this one recommendation came from Bill Gates? Well, if you're a Mac user or a PC user, it might change what you think of that, but nonetheless, that made a big difference, particularly if these came from elementary school children, this person's children. Well, what's going on? That's called the equality of the endorsement. So if I have my friend Ron, he's a professor at Berry College, and he's the recommendation. Well, you don't know Ron necessarily, so you need recommendations for Ron. Well, then you need recommendations for the recommendations, some of which could be Ron. Okay, can we go back to the web, please? Okay, but that's exactly the way they looked at the web, is that this is a web page, and an arrow means that I can get to it from the other web page. It links to it. Well, what they said is by linking to it, it's an endorsement. And you're trying to figure out the quality of those endorsements. You can do that via mathematics created by someone living 100 years ago. But today, they do it on the size of billion, and some say that now Google indexes trillions of web pages. Okay? All right, I want to show another sketch for you. Let me make sure I've got the timing right. Yeah. This next sketch just simply asks, what can I do with some geometric objects? So let's watch that. And there's a few uses of geometric shapes. Let me connect that really quick, then I'll teach you an illusion, and then I've got one more sketch for you. I'm going to take a little bit more time. It'll take me about, I think, about 5 after to do that. So that's called the sticky head for rather obvious reasons, using the geometric shapes. One of the places that you may have used geometric shapes before is in tangrams. Have you ever played this game? Some people haven't. You just take a square, you cut in these shapes, and then you're given a target image. What's interesting is how often people don't consider that math. They'll think, oh, no, that's not math. Why? Because there's no numbers. No, this is math. There's a whole field of math called topology, where you think through how some shapes can morph into other shapes. And then there's the whole field of geometry, where people use a lot of spatial thinking. This is actually very difficult for me. I have a hard time with this. Even with all of my movement and everything I do as an artist, that doesn't mean I'm good at this. I'm only good at this when I'm given this. And even then it's hard. Can you please put the pieces in these shapes to make that? Okay, hold on. And then I start working at it. But that's another form of math, and it is mathematical thinking, just like with the wall, where you're using spatial thinking. It's in a different way, but nonetheless, it's still using that. This is one way that people use geometric shapes, is in CGI characters. They create the characters within a computer, and then that's what they animate to be, for instance, students at Hogwarts in a Quidditch match. I couldn't think what to call them. And then, or for instance, the Avengers, or the new Thor movie. I haven't gone to see that, but I've heard that it has an amazing amount of CGI in it, with amazing having both positive or negative context, if you like that or not. This particular rendering is off of my web page. Oh, I'm sorry, that link changed. It's not WW anymore, but just put in Tim Davidson, math, Star Wars, or Yoda, and you'll find it. But you can create, this is made in MATLAB, but it has Mathematica code, so you could pull up a rendering of Yoda in Mathematica. The way they do that is you'll have the shape, then they'll determine what each little polygon will look like, and then they actually do what's called computational physics, physics via a computer, to determine what it looks like. And this is from a Pixar movie. This was a breakthrough movie, or short. They call them shorts in what they were doing. They also do this in science. This is a submarine. This research came out of Lawrence Livermore National Lab and was considered one of the biggest discoveries in the 1900s, over 100 years. It was one of the biggest discoveries, was being able to grid something so it looks this good in what they're doing. Another place that that's been used is to study how a soccer ball moves through the air. And here, this is actually the soccer ball. The grid is around the air, and in each grid, they're going to determine where the air is moving through it. So for that, really quickly, I want to teach you an illusion. And yep, I am going to go till, it'll be more like 7 after, but I'll do this illusion quick. Take your hand out and grab a ball, okay? And throw it up and catch it. When you throw it, the way you see the movement is with your eyes. So throw it up and catch it. If you don't watch it, then that's when you don't know where it went. So then you can throw it and have it hit you. Which if you think of what I just did, it's kind of an amazing thing. I threw it up, it landed, and somehow it just like stayed on my head, which is part of what you can do in mime. You can just let thing, and every so often, particularly like, I don't know, about an 8-year-old kid will go, how did that just stay on your head? Oh, because there's glue on it. I mean, it's like, you know, I'm throwing a ball with hot glue on it. And then, you know, so anyway. All right, so have your ball, throw it up, and catch it. Good. Throw it up one more time, and catch it. Good. Let's do one more thing. Grab 5 of them and bring them in. It's mime, so make them into a ball. Pick it up, and it's 5 times as heavy. Throw it up and catch it. Throw it up and catch it. Good. And then put it aside. That's a lot of fun to do with kids. There's a lot of things within education with kids that does what's called measurement. And that's a way to do measurement with children. I'll do it with kids where we get 100 of them. We can't lift it. Then we take it out, and there's 50. Can't lift it, and then there's 25. And you keep asking them how many. But I want to show you an illusion just very quickly. I won't do the full sketch with it. But I'll use each of you once, because I wasn't fair when I asked you that infinity question. That's, I'll go home and tell my wife. She'll go, why did you just pinpoint them like that? And I was like, I'm sorry, I don't know. Because I talked about ranking. I mean, I don't know. But I'll let you do this part. And if you don't want to do it, you can just say no. But believe me, this is a cool trick. You want to do it. So here we go. I've got this bag. And then I've got the ball. So I'm going to let you go first. Can you just stand up? And what you're going to do is you're just going to throw it right to me. Okay? All right. Okay, so just lob it to me. There it is. All right. So I'm going to throw it back. And when I go like that, that means you caught it. So make it look like you caught it. Ready? Okay, there you go, and there you go. All right, so throw it. There it goes. All right, now it's your turn. I'm going to switch over. Can you stand up? Okay, and I'll move a little bit farther back because I can guarantee you can throw it that far. All right, so here you go. Go ahead. And there it went. That was pretty hard, and so here we go. I'm going to lob that back to you. You ready? All right, here you go, and good. All right, I'm ready this time. And there we go, like that. All right, can you both stand up? I want to teach you a mime move. Okay, you stand this way. Good. You put your hands over your head, then you bend down, and people clap. Good. All right. You know how I'm doing this trick? I learned this from a Ringling Brothers Barnum and Bailey clown. Does anybody know what I'm doing? Yeah, I'm snapping my finger. And you don't have to know how to snap. It's just the maneuver. Like, sometimes young kids can't snap, but they got the idea. They're just not making a sound. So watch what I'm doing. Fingers go in, thumb goes out. Very important if you're doing this with kids, because they will put their entire hand in. It doesn't work, okay? Or someone will actually try to put their whole hand on the outside. So out and in. And then, you see it? And then it just goes in like that. And it looks quite real. The other one you can do, I didn't do this, so you go ahead and throw it to me. I'll do this really quick. So go ahead. Is that you can make it mime, and all of a sudden, you come in. Like that, and then you go from there. So that's really fun. The other one is when somebody throws it as hard as you do. I didn't want to do that because I'd been kind of unfair earlier. But if anyone else, if you ever see me do this with anyone else, you can say, he didn't do that with me because he was mean to me. And so, but normally when they throw it that hard, I don't make it go in the bag. I'll go, and then I come over and go, and then I throw it in the bag like that. So I didn't do that today. All right, I've got one more. Oh, really quick, I wanted to connect that to soccer. This will just take a sec. So this is the one we saw. But what does that mean, you're determining how a ball goes? It means you're figuring out how air travels over the ball. So what they were studying, this is engineers, not mathematicians. Engineers know a lot of math, so they are just like physicists. They're the mathematicians of their own kind. Every World Cup, they design a different seam pattern. And the balls do move differently through the air, given those differences. The same thing's used to study when you hear about cars moving through the air. They're doing the same thing with that. They do the same thing in sports. On the right, we see swimsuits that they were studying how they moved through the air when they were allowed to wear the full body swimsuits, which I think they're not allowed to use now. And here they were studying how the air moved through a stadium so that they had sufficient airflow. All right, I have one more sketch for you. This sketch uses a very simple principle. It just simply asks, what is it like to be the remainder? I think we all know, but nonetheless, let's watch this sketch and see it in a very fanciful, lighthearted way. Oh, you know, I think they turned the sound off. Okay, I'll do it. Give me a sec. Let me do it different. If you were my students, you'd feel perfectly fine that I look like this, so I just want to point out. This is just because you go to Elon. Okay. I'm sorry, we turned this off earlier, so let me do it this way. Can you hear it? Okay.
Chanson guimauve de Scalini s'en fout, mais il n'est pas chien et le lui rend bien, il est éclectique. Sonate ou java, concerto polka, il aime la musique. Le piano du pauvre, c'est le Chopin du printemps. Sous le soleil mauve, des lilas de Neugenres. Il roule le brin à ceux qui se plaisent bien, il fait des avances. Ravel ou Bachin, c'est déjà la fin, le plat qui recommence. La chanson guimauve de Scalini s'en fout, mais il n'est pas chien et le lui rend bien, il est éclectique. Sonate ou java, concerto polka, il aime la musique. Le piano du pauvre, c'est le Chopin du printemps. Sous le soleil mauve, des lilas de Neugenres. Il roule le brin à ceux qui se plaisent bien, il fait des avances. Ravel ou Bachin, c'est déjà la fin, le plat qui recommence.
And there you go. So really quick, one quick thing just to close. Because one of the biggest things for me in teaching is that I would like to believe that someday when you're sitting at a table and someone turns to you, a child, and says, you know what? I think I like math. That you have a story to tell that can affirm that love for them. That may be me too. That's why I studied it. But even if you've studied it, we need, as a mathematical community, to have stories to tell the world that show that there's a reason to learn math, whether it be bracketology, whether it be an infinite rope, whatever it may be. And that we also teach people that mathematical thinking extends far beyond numbers, and it extends far into our culture, making Google, making Sudoku, making many things possible, just like other fields enrich our lives as well. For me, that connection is made through mime and math. Why? Because that just happens to be two things that I know. So what I say to you is, what do you know? And look for how they're connected, because it may be you're the only one who will figure it out. Because I can pretty much guarantee I'm probably about the only one who would have figured out where mime and math connect, just because of the journey that I have. So look at your journey and figure out what it is. It took me time. I was doing mime and I was doing math, but connecting them was something that somebody else saw in me, not myself. Thank you, and enjoy the evening.